means environment protection, in which now this water remediation is there, smart absorptibility is there. They are also capable of self cleaning and self healing, enhancing their reusability and extending their operational lifetime. Now, even this iron prevention and promoting circular economy, these smart materials are engineered to facilitate the recycling and reuse of other materials. Even some polymers can be transformed back into their original monomers, allowing for easy reprocessing and reducing the reliance on virgin resources. Then sustainable technologies. Now, this energy harvesting and storage. These smart materials offer exciting opportunities for enhancing the efficiency of energy harvesting storage and solutions. These piezoelectric materials are also there. These materials convert mechanical vibration and stress into electrical energy, enabling this development of cell-powered sensors and devices that can operate without external sources. Then thermoelectric materials. These materials convert temperature difference into electricity, providing opportunities for generating power from waste heat or ambient temperature variations. Then shape memory alloys. These new materials are harvesting energy from temperature fluctuations by undergoing shape change and converting that heat into mechanical work. This property is exploited in various applications such as temperature controlled actuators and thermal engines. Then infrastructure and construction. These smart materials can enhance the durability and longevity of infrastructure projects. Then self-healing concrete. These concrete contain bacteria and comes of healing that can autonomously repair cracks, extending the lifespan of structures and reducing maintenance cost. Then semi-activated variable geometry structures. These enable structures like aircraft wings or architectural elements to adapt their shape in response to changing environment conditions. Now, this sustainable agriculture, because of these responsive polymers and nanocomposites, these are explored for applications in agriculture, such as smart super absorbent hydrogels that efficiently manage water resource. These smart materials are now revolutionizing renewable energy systems by enhancing efficiency, durability, and adaptability. These are responding to stimulus like temperature, light, or pressure that are enabling breakthroughs in energy harvesting and storage. Now, these key advancements are there, that is enhanced energy harvesting. Means these piezoelectric materials are now used in wind turbine blades and hydroelectric power plants to convert mechanical energy into electrical energy. Then shape memory alloys. This like nitinol, this is new material. These are embedded in turbine blades for aerodynamic efficiency and in road surface for energy harvesting from vibrations. These thermoelectric materials such as silver antimony telluride that can convert waste into electricity. And nanotechnology is also improving energy storage and conversion efficiency. And graphene, this is also now new emerging material is coming, which is able to explode for green hydrogen storage. Because this green hydrogen, now we are having green hydrogen trains in India. This model prototype is ready in Northern Railway between Jind and Sonipat railway station, 91 kilometers distance. And these trains will be now working, means functioning on this green hydrogen. Of course, green hydrogen vehicles are also functioning, green hydrogen buses, green hydrogen two-wheelers are also working in metro cities. And this is emerging as the new emerging renewable fuel. Even Honorable PM Sir, Honorable Shri Narendra Bhai Modi Sir has inaugurated this green hydrogen hub near Visakhapatnam that is saving 1 lakh tons capacity, storage capacity of green hydrogen. Then phase change material. These are incorporated into solar panels to manage temperature and improve the light absorption. Even now, new developments are going on in which now moonlight can be converted into power. Up till now, we have read that the solar panels or solar radiation is used for power generation, but new developments in Japan are going on in University of Japan that this moonlight will be used for power generation. Even now, The new developments yesterday, I have read one news on the WhatsApp channel. Ki, in that case, this up till now we were requiring this radiation, means sunlight. What it should be daylight, bright sunlight. But now these solar panels are made in that way. Ki now these cloudy. Consider example of today. Throughout India, we are having now cloudy season. Means monsoon is going on throughout India. And during these 3 months, nearly 3 months, we are having this cloudy environment throughout India. These solar panels can be functioning, or these will be generating power when clouds are there in the sky. Means there is no need of having bright sunlight. Even cloudy means environment, these solar panels can function and operate that. Then smart grids and microgrids are also there, in which these smart metering systems are these are enabling real-time monitoring and management of energy demand and supply, facilitating the integration of renewable energy sources and smart materials. These are crucial for building decentralized power systems and optimizing energy storage. Then self-healing and self-cleaning materials. This nowadays self-healing concrete, it is being developed to increase the lifespan of infrastructure and reduce the maintenance cost. These are used in wind power generation because this wind power, when these are commissioned in the deep sea or on the river sides, the corrosion effect is very high. Hence, the life of that concrete structures or that cement structures, this becomes comparatively weak. Nowadays, this self-healing concrete is used so that this life of these windmill structures can be enhanced, which are commissioned in deep sea and as well as on the river beds of the means adjoining areas, because this because of moisture, and this corrosion effect is more as compared to hilly areas of windmills. Then self-cleaning surfaces. In these solar panels, they reduce the need for manual cleaning and improve the energy output. Means now these new surfaces are made in which the dirt, dust, or leaf, whatever these raw material, outside materials are deposited on the solar panel, they got automatically cleaned. No need of any human person to clean that. Nowadays, these AI-driven optimization systems are used in this green energy. This AI is used to optimize the design and performance of smart materials for renewable energy applications. Even machine learning helps in the high throughput screening of new materials for energy applications. These are some of the applications, that is solar energy, that is smart coatings on solar panels, advanced solar tracking systems, and phase change materials for low temperature regulation, energy efficiency and performance. And wind energy. These shape memory alloys in turbine blades improve aerodynamics and piezoelectric sensors, which monitor blade stress and predict the maintenance needs. Then hydropower. These piezoelectric mano generators can harvest energy from water currents. Then building material. These smart windows and self-healing concrete contribute to energy efficiency and durability. These are different smart materials in energy harvesting, that is photovoltaic efficiency enhancements. These perovskite and bifacial solar panels. Nowadays, these bifacial solar panels are introduced. Means on both sides they can generate the power. Even nowadays, these solar panels are put on the walls of the building. Up till now, we were commissioning these solar panels on the rooftop, but now these new developments, new materials are coming in which solar panels are fit and commissioned on walls of the home or these buildings. So these perovskite solar cell offer high power conversion efficiency and potential for lower production cost. And bifacial solar cells increase energy output by capturing light from both sides. Then nanotechnology and coatings are also used, in which quantum dots, these enhanced light absorption and hybrid nano coatings, which offer self-cleaning and anti-reflective properties. Then adaptive photovoltaics. These AI optimized hybrid PV cells can adjust their properties based on environmental conditions for maximum energy generation. Then energy harvesting from mechanical sources, means piezoelectric and triboelectric materials. These piezoelectric materials generate electricity from mechanical stress, useful for harvesting energy from vibrations. These triboelectric nano generators utilize friction for energy generation suitable for various applications, including wearable electronics. Then the shape memory alloy integration. This combining shape memory alloy with piezoelectric materials can improve energy production and lifespan. Then other harvesting and conversion mechanisms, in which these electromagnetic generators are used, which convert mechanical motion into electrical energy. These thermoelectric materials are used, which generate electricity from temperature gradients, promising for converting waste heat. Then smart materials in energy storage are also nowadays used. These enhanced batteries are used in which of this in electric vehicles we are now using this electrical battery and energy storage. These advancements in materials are improving lithium ion battery performance and enabling technologies like solid state battery and graphene based electrodes. Because the main problem of these conventional electric vehicles batteries is key heat dissipation. Because of less the heat dissipation and earlier charging times, the improvement or performance of electrical vehicle was comparatively slow or low. With the help of these advanced materials, we can have more means heat dissipation capacity means this will not be burned easily because during May, at least in central India, when temperature is nearly 47 degrees centigrade, and this continuous running of electrical vehicles. Suppose any vehicle is running for 2 3 hours in this central India in temperature 47 degrees centigrade, the chances of catching the fire are comparatively more. Some cases have happened in Nagpur, in which these electric vehicle batteries, two-wheelers batteries, they captured fire because of more heat dissipation, more heating. So hence now with the help of this introduction of these smart materials, this heat dissipation capacity is improved, and as well as life of these machines and these electric batteries, this is also enhanced. Then supercapacitors, these materials like carbon nanotubes and graphene are used for high power density and fast charging and discharging. Even I have read today these Chinese they have developed their technology in which this car battery is charged within 36 seconds. Means within half minute. Today I have read this. China have made that electrical vehicle charging infrastructure in which this car battery can be recharged within 36 seconds. Means imagine so fast up till now. This is the so fast. Then phase change material. These store and release thermal energy used for thermal energy storage and improving the thermal stability of PV panels. Then these smart materials for energy management are also there, in which these smart coatings are used, which thermochromic materials can change color with temperature, potentially reduce cooling loads. Then smart building materials, that is incorporating materials like transparent woods or straw, support sustainable building and reduce energy consumption. These are some of the innovations in solar panel design and materials. This is the huge structure in which these solar panels are commissioned. And here we are finding this three-story building is there. Now, as the world attempts to reduce the carbon footprint, solar energy is proving its importance. This development of solar panel design and materials is significant component in increasing solar energy efficiency. Up till now, we are having this solar efficiency. It is not that much significant. Maximum energy efficiency generation from solar panels it is nearly 29.7%. But the new developments in Japan and Stanford University in US, they this of course this is in prototype stage. They have made the solar panels which can have solar efficiency up to 34.8%. Means nearly 5% more it will be generating, having that more efficiency. But this is under prototype. Still, it is to be made commercially. But anyhow, these developments are going in which we can have more solar efficiency. The main benefit of these solar panels or solar chips is that no any fuel cost is involved in that. Only infrastructure cost is required, and that is in initial. And having solar panels, it's like nearly 8 to 10 years. Means up to 10 years there is no any problem of any maintenance or that. Only just we to clean that their surface. Otherwise, everything is okay in that. Means this is the best thing. Solar power we are having nearly in India, almost all parts of India, we are having nearly 280 days bright daylight sunlight out of 365 days. except these 3 months of monsoon. Remaining 9 months, we are having clean, clear, bright solar sunlight. Hence, this solar sunlight is used for optimum power generation. This is the main benefit for India. These recent years have a tremendous advancement in solar panel technology, creating creation of novel components and layouts, including bifacial panels and thin film solar panels. I mean, just like very thin, just like hair. Our hair size these are so thin solar panels, solar cells. These panels are now more resilient, adaptable, and efficient. Even now, so foldable solar cells are made now. Solar panels are made foldable, which can be folded. This has created new possibilities for using solar energy into other forms of infrastructure. These are developments of solar panel technology. These bifacial solar panels, which can produce energy from both sides of panel and increase the energy efficiency and lower the overall cost per watt of a power generator. Due to their great efficiency and low cost, these perovskite materials have attracted a lot of attention. These solar cells made of this perovskite material have potential to be more efficient than silicon-based solar cells. These advancements of solar panel technology also paving way for incorporation of solar energy into different infrastructures, including transportation and residential and commercial structures. Nowadays, even solar cars are made. Even solar ships I have seen in some of the news channels in which these now ships which are in sea. These are working on solar panels. Even these new developments are also going in which aeroplanes are also, of course, these are on prototype basis. These aeroplanes are made of solar panels and these are running on the solar power. This has been made visible by technology advancement like solar powered electric cars and photovoltaic systems. Just like we are now having electrical cars, even students projects, majority of the student projects are they are now in college. They are making the solar powered two-wheeler, solar power sprinkler, solar power tractors, solar power cars. These are the most popular solar power cars. To this sense, these are new development and these are successfully running, functioning without any trouble. This perovskite solar cell, these are having up till now 25% theoretical, had been demonstrating enormous potential, but in some cases this is giving 29.7%, majority of the cases. These tandem solar cells are also there. These boost the effectiveness of solar panel. These solar cells integrate two or more components. These studies have proved that combining silicon and perovskite materials can attain energy levels above 30%. Then bifacial solar panels, these are producing energy from both sides. Then organic solar cells are also made, which are lightweight, flexible, and inexpensive. Means these are cheaper to make organic cells constructed from carbon-based materials. These most recently have concentrated on increasing the stability and efficiency of organic cells. Then this building integrated photovoltaics. With this technology, solar panels are incorporated into building components including walls, windows and roofs, which lowers total cost and improves the aesthetics of the solar energy. This most recent study have concentrated on creating new components and manufacturing procedures to increase the affordability of this BIVP. These are emerging solar panel materials and their properties. This perovskite, this is high efficiency and low cost. And this solar cell made of this are having potential to be more efficient than conventional silicon-based solar. And organic polymers, these are often referred to as plastic solar cells. These are lightweight, flexible, and inexpensive to make. Means these are economical in making. Then quantum dots are also used. These are high efficiency solar cells which are made using these minuscule quantum dot particles of semiconducting materials. These traditional silicon based solar cells are less efficient, hence, these are comparatively more efficient. Then CIGS means copper indium gallium selenide. It is newly developed thin film solar panel material that is having potential for cheap manufacturing cost and excellent efficiency. This lightweight, flexible, and available in wide range of Forms are the characteristic of these CIGS panels. And graphene, nowadays graphene is emerging as the promising material because graphene stock we are having this raw material we are having in good quantity in India also. Hence, this is emerging as this new material. This is two-dimensional substance with exceptional electrical and optical qualities. Graphene is proving valuable in development of solar panel technology. Integration of graphene into solar cell is increasing effectiveness. These new solar materials have the potential to completely change the solar energy optimization. These are some innovations in solar cell manufacturing in which 3D printing is used. Just like this, we are having 3D printing in now houses also. I have seen one news channel in which this railway station was made within 48 hours with the help of 3D printing in Germany. Means this is having so promising technology. With the help of this 3D printing, this enables the manufacturing of intricate geometrics and exact control over material composition, which is possible to design and make solar cells both extremely effective and unique. Then roll to roll printing means printing from roll to roll is continuous manufacturing technique that allows for quick and inexpensive mass manufacture. Atomic layer deposition. This is manufacturing process that makes it possible to produce extremely thin films, which may be utilized to produce highly efficient solar cells with little material wastage. This perovskite inkjet printing. This makes it possible to print perovskite based solar cells directly into variety of surface, expanding the potential use for solar energy. Then smart manufacturing. This smart manufacturing employs digital technology to streamline the manufacturing process, thus making lower wastage and boosting productivity of solar cells. This they have made technological advancements in solar cell, lowering the cost of energy and opening the large use for uses. Because even a new scheme is also launched by Honorable PM Sir, PM solar panel scheme, in which you just we have to give the space, rooftop space, to Ministry of Renewable and New and Renewable Energy Sources. That department is commissioning these solar panels under PM solar scheme, in which we have to give just only the space. Remaining infrastructure is made provided by this agency, these government departments. And in that, when we are generating more power, we can sell that extra power to grids. Means which are electricity means authorities in all states. We are having these state electricity boards. So suppose more power is generated, then we can sell that extra power to the grids. Means these developments are also going on. These are different breakthroughs in solar panel efficiency, in which this efficiency rate of 28.9 was attained in 2018. At present, I was telling you 29.7 is this optimum efficiency of solar power. And now new developments are going on, in which now 34.8% is, of course, this is in prototype stage. The new developments which is here, these solar cell, these can be used and their efficiency is reaching an efficiency rate of 47.1%. This development is going on in US National Renewable Energy Laboratory. Means they are working on this. If this 47.1% efficiency is achieved from solar cell, then there will be no any problem of power or electricity shortage in India. Even nanostructured materials are also investigated by researchers as a way to increase solar panel efficiency. This I was telling you, which this University of Michigan they have created the solar cell in 2020, which was having this nano structure materials with efficiency 29.1%. But now 29.7% is comparatively general. Means all panels they are having 29.7%. But with one condition, one prevention we have to take, all these solar panels should be clean and dry. If there is any dirt, dust, or moisture, or any leaf, or any other foreign material is deposited on this panel, then its efficiency will be lowered. Hence, we have to take that only one that precaution. Hence, we have to clean that once in a day, at least in once in a day. In morning, we can change that. Within 5 minutes, we can clean that. There is no much in that problem in that. Then, what will be the future of the solar panel technology? This future of solar panel technology is offering new and inventive strategies to increase the effectiveness and accessibility. This creation of novel materials for solar panel is also one of the area for focus. These perovskite solar cells have proved lot of potential for improved efficiency and cheaper production. Should I share one video with you? I'm sharing one video with you so that we can have how this developments at world level is going on.
Imagine solar panels so powerful, so flexible, and so cheap it could turn windows
This is
into power
visible.
generators. It could coat your phone to charge
Video is
itself
visible,
and
no?
revolutionize how we power our homes. I know a
Yes,
lot of
sir.
people say this sounds
Yes,
sci-fi
sir. It is
movie.
visible.
It's real, and it's called perovskite. Being in the renewable energy sector for many, many years, I've been following this technology. And what I'm seeing right now is absolutely mind-blowing. We're talking about solar cells that could disrupt the multi-hundred-billion-dollar global solar industry and change everything we know about solar energy. Hey guys, and welcome back to my channel. In today's video, we are diving deep into perovskite solar cells, what they are, why scientists are obsessed with them, and how they could potentially change the game completely. Now make sure to stick around because by the end of this video, you will understand why perovskites might be the biggest energy breakthrough since silicon. We're going to cover how these materials actually work, compare them to traditional silicon solar panels, look at the real companies already deploying this technology right now, not in 10 years, but today. And we'll also dive into the challenges that still need to be solved. This topic goes definitely beyond a 10-minute video, so I'll make sure to dive deeper into various aspects of perovskite's technology in the upcoming content as well. Make sure to leave them some comments with ideas after you watch this video and give me some feedback on the way I do these videos. Now, if you like this one, make sure to subscribe to the channel as well so that you do not miss out on future energy breakthroughs. And it helps me so much, so thank you. Speaking of, since the 30% tax credit could potentially be gone before the end of the year, now is the time to look into solar pricing or storage pricing as well. So if you're in the DFW area, make sure to reach out to me. My contact information is going to be in the description below. But if you're not in Dallas area, I can help you find a local installer in your area that is reputable. So you have my contact in the description. But now let's get back to the video. So let's start with the basics. Perovskite isn't just a single material. It's a whole class of materials that share a specific crystal structure. The perovskite mineral, calcium titanate, I can't say that word in English, I tried, but it was discovered in 1839 in the Ural Mountains and named after a Russian mineralogist, L.A. Perovsky. For well over a century after that, this class of materials was primarily of academic interest only, studied for their unique properties, but not really widely considered for any groundbreaking applications like solar energy. It wasn't until 2009 that researchers made the initial step demonstrating that organic lead halide perovskite could indeed absorb light and convert it into electricity, though with a pretty modest efficiency, and I mean pretty low, at 3.8 PCE. However, the turning point is when the perovskite started gaining sufficient traction was actually in 2012. A major breakthrough that year involving the use of solid-state components dramatically boosted efficiency and stability and started a unique rush of research and development. Since then, the progress has been pretty explosive. These modern synthetic versions, typically a mix of lead, halide, and organic compounds, can absorb light incredibly well and turn it into electricity far more efficiently than traditional silicon, and at a fraction fraction of the cost. To put it simply, perovskites are like a solar equivalent of going from dial-up internet to 5G overnight. They're lighter, cheaper, easier to produce, and far more versatile than the stiff, heavy silicon panels that we see on the rooftops today. So let's compare the absorption efficiency between silicon and perovskite. So lab tests have shown single junction perovskites reaching over 26.7% efficiency, matching the best silicon cells. And when combined both in tandem solar cells, that number jumps past 34%. That's huge. For context, the most residential solar panels I installed today operate at around 20 to 22% efficiency. So we're talking about a significant jump in power generation from the same amount of footprint. So what's the catch? I will get there, I promise. Now, here's where it gets really interesting. Unlike silicon, which requires high temperature processing and expensive equipment, perovskites can be made using low temperature, low cost methods like inkjet printing, spray coating, or roll-to-roll manufacturing, similar to how newspapers are printed. Now, this means that factories could literally print solar panels onto flexible plastic or glass. It opens up an incredible design freedom: solar windows, solar backpacks, solar cars, solar clothing. So let's break down how these are actually made. So one method involves layering specialized materials on a substrate, typically glass-coated, with a transparent conductive layer. First, an electron transport layer, like titanium dioxide, is applied to help move electrons. Then, a solution coating perovskite materials is deposited, often by spin coating, and heated to form a light-absorbing crystal layer. Next, a whole transport layer is added to carry positive charges. Finally, a metal electrode is applied on top. The whole structure is sometimes encapsulated to protect it from moisture and light damage. So imagine solar panels you can roll up like a yoga mat. That's basically perovskite. Okay, so if perovskites are so amazing, why don't we see them everywhere yet? Well, there's always a catch. So here's the main challenge: stability.